What if AI could do in 20 minutes? What takes a trained architect 3.5 hours, with fewer errors?
This 9-minute video explores exactly that. We are standing at the edge of a new era in design, where AI doesn't just assist you. It thinks, plans, and builds alongside you. But here's the real question.
When machines handle the heavy lifting, what is left for the human mind? The AI expert and engineer Manish Khapare has answered, and the answer might surprise you. Watch the video till the end and find out why he says the most powerful tool in the AI age is still you. Now, over to video.
Every architectural project begins with a conflict. On one side is the subjective, aesthetic vision. On the other side are the rigid demands of physics, finite budgets, and strict building codes. For years, artificial intelligence in design struggled to bridge this gap. The early integration of AI was dominated by single-agent chatbots that generated impressive, atmospheric concept art. But these outputs were completely unbuildable. They were statistical guesses at geometry, lacking structural logic. Professional practice now operates on agentic AI. Agentic AI refers to a system of specialized, coordinated AI models that autonomously plan and execute multi-step workflows. Instead of generating random visual options, these systems proactively forecast the structural integrity, environmental impact, and financial performance of a design. This chart measures baseline efficiency. A solo human designer averages 3.55 hours to complete the work, carrying an error rate of 12.3%. When executed through a multi-agent AI pipeline with optimized prompting, completion time drops to 18.7 minutes, and the error rate falls to 8.2%. This 11-fold speedup relies on 4 specific computational pillars working in sequence: generative AI for spatial ideation, computer vision for site monitoring, natural language processing for code compliance, and machine learning for structural forecasting. To understand how these systems coordinate, we can reverse engineer a modern architectural curriculum. By tracking how a student builds a project from concept to construction, we expose the exact multi-agent design pipeline used by top-tier firms. Modern architectural practice depends on the engineering of comprehensive, automated design pipelines that span the entire project lifecycle. The pipeline activates at the very beginning of a project, starting with an empty studio space and a raw, unstructured client brief. To translate that brief into spatial concepts, designers deploy custom LoRAs. Low-rank adaptations, or LoRAs, are lightweight training techniques that inject specific stylistic data into a massive pre-trained AI model without rewriting the underlying system. A designer does not need thousands of examples to teach the AI their style. By feeding the model a tightly curated dataset of exactly 5 to 9 high-quality reference images, a studio trains the system to perfectly replicate their distinct proprietary brand voice. Once the atmospheric concept is approved, the system immediately strips away the aesthetic layer to calculate exact functional dimensions. Here is a top-down view of spatial AI processing room dimensions. The system simulates thousands of permutations, dynamically rearranging walls and furniture to avoid traffic heat maps while maximizing natural light. Because every element is tied to structured data, these adjustments instantly generate exact quantity takeoffs and bills of materials, an itemized list of raw materials required for construction. Historically, producing a functional test fit and calculating its procurement cost required weeks of manual drafting and spreadsheet management. The multi-agent pipeline extracts this data instantly. Early-stage interior design is entirely quantifiable. Concept generation and spatial logic happen simultaneously. Moving from the layout of interior rooms, the computational scale expands to verify the physical skeleton of the building itself. Traditional engineering relies on finite element analysis, or FEA, to confirm if a design is safe. FEA is a highly accurate computerized method for predicting how a structure reacts to physical forces, but it is incredibly slow, often creating a severe bottleneck late in the design process. To bypass this delay, the pipeline employs predictant structural metamodels. Metamodels are highly efficient machine learning algorithms trained on massive datasets of previous FEA simulations. They allow architects to forecast load behavior and material costs instantly, long before formal analysis begins. Looking at this structural beam, we see the specific variables the AI processes. It calculates the optimal member size by balancing span length, L, material strength, MS, and load intensity, Q load. As the predicted load increases, the system automatically thickens the beam to maintain safety margins. The exact same predictive mathematics governing the steel are applied to the building's environmental impact. The system ingests local climate data, running continuous simulations to determine the most thermodynamically efficient insulation and exterior shading. This proactive modeling shows a consistent reduction in power consumption, improving energy efficiency by up to 40%. These same predictive models scale outward, analyzing macro-level urban planning constraints, site feasibility, and complex municipal zoning laws in real time. Physics, structural safety, and environmental impact act as proactive design drivers at the beginning of the project, rather than reactive corrections at the end. Once the physical behavior of the structure is confirmed, the workflow shifts to the legal bureaucracy of construction documentation. This phase carries a massive liability risk known as silent skill erosion. This occurs when human architects blindly trust generative AI outputs and issue unverified plans, failing to validate the machine's work against local safety and building codes. To manage this risk, firms utilize multi-agent orchestration, building a central corporate Jarvis to route data through specialized nodes. First, the extractor agent isolates precise dimensional data from the 3D model. This raw data passes to the validator agent, which cross-references dimensions against a live database of municipal building codes, flagging legal discrepancies. Once validated, the final node formats the information, outputting a fully compliant, standardized PDF construction document ready for contractors. These orchestrating agents also interface directly with a firm's business software, autonomously analyzing the construction documents to forecast potential timeline delays and budget overruns before ground is broken. Simultaneously, the validated 3D models are instantly converted into real-time augmented and virtual reality walkthroughs for final client presentations. The multi-agent system systematically eliminates the operational friction between creative intent and legal, code-compliant execution. When we evaluate the fully integrated multi-agent tech stack, the scale of the compounding advantage becomes clear. This table returns to our core performance metrics. The pipeline reduces a complex task from 3.5 hours to under 20 minutes. While an 11.4x speedup transforms project timelines, the true return on investment is the drop in the error rate. Pushing errors down to 8.2% drastically minimizes structural failures, costly legal revisions, and physical material waste on the construction site. Access to this compute-bound infrastructure democratizes the built environment. Small, agile design studios can now analyze data and execute deliverables at the scale of massive multinational engineering firms. Multi-agent systems handle the intense computational heavy lifting of the AEC industry, reserving human capacity for high-level conceptual reasoning and strategic oversight. To enforce this, modern curriculums require a plausibility trap audit. The plausibility trap is the tendency of AI models to generate outputs that sound highly convincing, but are factually or physically incorrect. Human designers are strictly required to peer review the AI's step-by-step reasoning paths to catch and correct these hallucinations. Operating the pipeline safely requires rigorous requirement architecture. Designers must command the agents using strict, mathematically bounded constraints, entirely abandoning vague, adjective-heavy prompting. Artificial intelligence provides the computational engine, but the human remains the essential thinker, analyst, and strategist required to build the future.